Hello and welcome back. So this is going to be the part 2 of the first lecture, if you wish. And I understand that in the first lecture my voice may have been a little on the lower side, and there was some background noise as well. So hopefully in this one and all the next lectures we would be able to get rid of the background noise. And I will try and speak a little louder so that I am more audible. So what I have been harping on for quite some time now is the fact that relativity. So what we did last time is that I told you that you would be able to see that electricity and magnetism are not separate phenomena, and they're manifestations of the same electromagnetic force. And I told you that this you can see more clearly within the framework of the special theory of relativity. And what we did is then we did some thought experiments, or also known as Gedanken experiments in German. And I showed you things that you have probably already seen a lot of times, that things like, the very significant features of the special theory of relativity, namely the relativity of simultaneity, which shows you that two events that are simultaneous in one inertial frame are not in general simultaneous in another. The second one that we showed you was time dilation, and it sort of manifested the fact that moving clocks actually ran slow. We also showed you something called Lorentz contraction, which meant that moving objects are actually shortened. Now, in this short lecture that I'm going to give you today, what we will be focusing on is using Lorentz contraction to understand magnetism from something that where you would have thought that. Okay, let me rephrase. What I want to say is that today what you will see is that what electrostatics and special theory of relativity inexorably leads you to something like a magnetic force. So let's start. So we are going to call this magnetism from relativity. And so we were going to start off with the diagram that I've shown you. Okay, so another thing that I propose to do from now on is that instead of boring you by trying to draw diagrams in the lecture itself, I shall try and have them for you on the screen. Okay, so what we are going to do is we are going to start off with a current carrying wire, and there is going to be a moving charge. So this cylinder that you see is going to be this current carrying wire, and there is going to be a point charge which is Q, which is at a distance s from this wire. Okay, so let's see let's give you a few more details. So this wire has positive charges, a string of them, that are going to be moving towards the right with a velocity v. So this, let me try and show you this. So, okay. So let's try and point with this guy. So we will have this object. This is a line charge. String of positive charges that are moving towards the right with a velocity v, and we are going to superimpose on it another string of charges. Now with moving towards the left, these are going to be negative charges. This is this line here, and that is going to be moving towards the left with the same velocity v. So these charges on both these wires, if you wish, are close enough so that you can treat them as a continuous line charge, So we are going to call the charge density line plus lambda on this, and there's going to be a minus lambda on the one with the negative charges. Since these are superimposed on each other, what we are going to have is the following. So the net charge of the whole wire is going to be 0. We have a net charge of the wire equal to 0, but also a net current in the wire which moves to the right with magnitude I, which is given by twice lambda into V. Okay. Now, as I said, we are going to place a charge Q, which is at a distance S from the wire, and this is going to be moving to the right with a velocity V. Okay. So we have a charge Q at a distance S from the wire. This moves with a velocity u, and we will take u to be less than v. Okay. So what is going to happen now? What is going to happen is that since there is no net charge on the wire, so no net charge on the wire, so this means that the electric force on Q is equal to 0. So all of this is happening when we are in a frame which is at rest with the whole thing, right? Okay. So when we are in a frame S which is at rest, and this is all happening there. So what we are going to be doing now is that we are going to move to a frame which is going to move to the right with a velocity u, such that the point charge q is at rest in this frame. Okay. So move to frame S bar. So this S bar moves to the right with a velocity u. So q, the charge q, is at rest in the frame S bar. Very good. Now, since S bar moves to the right with a velocity u, the velocities of the positive and the negative lines will now change, right? And by Einstein's velocity addition formula, the velocities look like the following. So velocities of positive and negative charges, negative lines if you wish, lines now change and they are given by V plus minus, which is V minus plus U divided by 1 minus plus V U by C squared. Remember that we are moving to the right. So, the velocity of the plus charges has to decrease. Okay. So, V minus is greater than V plus. So, what does this mean? So, this essentially means that the Lorentz contraction factors on both cases, on both the lines will now not be the same. So, Lorentz contraction, since V minus is greater than V plus, what is going to happen is that Lorentz contraction of the spacing between the negative charges is going to be much more than that between the plus charges. So, spacing between negative charges is much more than that between positive charges. Okay. Hence, what is going to happen if we look back at the figure, you see that the charge density on this of the negative negative wire if you wish, increases. And in this frame, and in this frame, the wire would carry a net negative charge. So, this is a very surprising thing. So, what was neutral in one frame has changed into a charged object in another frame. Okay. So, now the wire actually carries a net negative charge. So, let us just try and put these in terms of equations. So, lambda plus minus is equal to plus minus of gamma plus minus into lambda naught, where gamma plus minus is given by 1 minus V plus minus squared by C squared whole to the minus half. Okay. So, this is where we are invoking what we learned in the last class, that is, so if there's something which moves, then so moving objects are actually shortened. Now, what you have to keep in mind is that you had this lambda naught. So, lambda naught is the rest charge density, and remember that we had started off with things which as you will see out here, the charge density here was lambda, and so this had to be, so the lambda naught is the charge density of the positive line in its own rest frame. This is of course not the same as lambda because this was already moving at a speed v in the initial frame. So let me just clarify what lambda naught is. Lambda naught is the charge density of positive line in its own rest frame. Lambda naught is not equal to lambda, what we started out with, because in S, this was already moving at speed v. So there is a factor of gamma again between lambda and lambda naught. So lambda naught is gamma times lambda naught, where gamma here is given by just 1 minus v squared over c squared. That is the initial velocity. Okay. So now what we want to do is we want to put gamma plus minus in a simple form. This is just simple algebra, which I'll leave to you guys to do. So lambda plus minus is just given by, once the dust settles, it's just gamma into 1 minus plus uv by c squared by square root of 1 minus u squared by c squared. So now the net charge in S bar is going to be lambda total, which is lambda plus lambda minus, which is given by lambda naught into gamma plus minus gamma minus. And again, a little bit of algebra just brings you that this is twice lambda u into v by c squared into square root of 1 minus u squared by c squared. If this is lambda naught, so we have come to this very, very startling conclusion that a current, so let me try and write this in blue for you. So a current carrying wire which is neutral in one neutral electrically, sorry, let's erase this, which is electrically neutral in one reference frame, inertial reference frame, due to unequal Lorentz contractions becomes electrically charged in another inertial frame. So this is indeed a very, very surprising thing when you say this. At first, it's going to appear like a jolt to you, but this is what is going to happen. This is sort of the nature of special relativity playing a role. So this line charge lambda total sets up an electric field. So electric field is given by E is lambda total. So if you are a distance s away from it, as you guys know very well, this is 2 pi epsilon naught into s at a distance s from it, from the wire. So if you are at a distance s from the wire, there is an electric field lambda by 2 pi epsilon naught s. So now if you want to look at the force on a charge q in the s bar frame, so force, electric force, okay, so electric force on the charge q in the S bar frame is SF bar is QE, which is given by minus lambda V by pi epsilon naught C squared S and 1 minus u squared by c squared. We've just put the things in. And so this is going to be the electric force on the charge q in the frame S bar. Very good. Now what you can imagine, what you can very clearly understand is, so this is a force. So if there is a force in a frame S, you can transform this using Lorentz transformations to what the force will be in another frame S primed. This is an exercise that we are not going to, this is an exercise that you will be doing. I'll give this as a homework in the upcoming tutorials that I will be assigning to you people, exercise sheets that I will be assigning to you people. For the moment, we are going to not derive this. What is going to happen is that we will quote this result. So now you're given the force in the frame S prime, and we want to find out the force in another inertial frame S, which is with respect to S bar is going to be moving at a speed minus u. So the force in frame S is given by F is equal to root over 1 minus u squared by c squared, your favorite factor again, so that's a gamma F bar. And so this is something that you will to be done in tutorials. And this is going to be, so let's just write this down. So what we have to do is we have to strip F bar of this factor of 1 minus u squared over c squared. So what do we get? We get minus lambda V by pi epsilon naught c squared into u q by s. Now let's put in, now use c squared is equal to 1 over mu naught epsilon naught. And remember that the charge that we had was given by twice lambda V. So this F now it takes the following form. This is minus QU into mu naught I by 2 pi S. Now what is mu naught I by 2 pi S? Mu naught I by 2 pi S, this factor that we have out here, this particular factor is simply the magnetic field of a long straight wire at a distance s from the wire, of a long straight wire at a distance s from the wire. So you can see, so this and this whole thing, so this, the expression of f, is precisely what the Lorentz force law would give you. In system S. So what have we seen? This particular analysis provides us with an explicit demonstration of how an electric force in one frame can be interpreted as a magnetic force in another frame. All right, so this is actually very striking, and hence I thought that it would be good for you to see this firsthand before we go on to do more mathematics. And so another thing that I want to really emphasize. So let's just recap what we did. So we had a system. We had a system where we had a wire, we had a long wire, and we had a string of positively charged particles which were moving to the right with a velocity v. And those were close enough to be approximated by a line charge, and that line charge was plus lambda. We superimposed on it a string of negative charges moving in the opposite direction, and that had the same line charge, but with a different sign. So that was minus lambda. And when we were looking at this system, so this was a system that was electrically neutral, but it had a net current which was moving towards the right, and this was twice lambda v. And we wanted to look at the force on a charge q, which was sitting a distance s away from the center of the wire and also moving to the right with a velocity u. The first thing that we noted was, since that the wire was electrically neutral, there was no electric force on q. And then after that we moved on to another frame which was moving towards the right with a velocity u, such that q, the charge q, was at rest in this frame S bar. Now, since there was a frame which was moving towards the right with a velocity u, the velocities with which the plus charges and minus charges were moving would change, and these would change such that v plus minus became v minus plus u by 1 over 1 minus plus vu by c squared. And so v minus would be greater than v plus. Since v minus was greater than v plus, the Lorentz contraction factor of the spacing between the negative charges would be much more than that between the positive charges. Hence, in this frame, negative charges will be closer to each other than the positive charges. So lambda minus, so this is going to result in the fact that the wire, which was previously neutral in the frame S, no longer remains electrically neutral in the frame S bar. So we estimated what the change, what exactly was the negative charge associated with it. So this lambda plus minus was given by this usual gamma factor acting on lambda naught. You had to keep in mind that this lambda naught was a charge density of the positive line in its own rest frame, so it was not the same as the lambda that we started off with. There was another factor of gamma out there. When the dust settles, we found that lambda total was given by an expression which is highlighted here. So this was the expression of lambda lambda total, and so what we found, again re-emphasizing the fact that a current carrying wire which is electrically neutral in one reference frame due to these unequal Lorentz contractions becomes electrically charged in another frame. Since this was the total charge, you could associate an electric field to this at a distance s, and then you could just find out what the electric force on Q is in this frame S bar, and this was given by another factor, that this was given by just multiplying these two things, and this is what we have. Now, since there is a force in the frame S bar, there has to be a force in the frame S. This can be found by doing Lorentz transformations, the details of which you're going to work out later. But for now, you have to take it from me that the two are again related by a factor of gamma. So F is equal to 1 minus u squared over c squared into F bar. So this is something that you'll find out later. And that means that you find what the force in F is, force in the frame S is. So this F is non-zero, but you have already seen that there is no electric force in F in the frame S. So this force F has to have some particular, some other origin, if you wish. Now, if we write it down and use the fact that c squared is 1 over mu squared epsilon mu naught epsilon naught, and the fact that the charge is current is given by twice lambda v, we get to an expression that we really understand well. It just shows that the F, the factor of F that we have found here in this equation, is related to is exactly what you would have got for the Lorentz force when we consider a magnetic field of a long straight wire at a distance s from the wire. So what we have found, to re-emphasize again, is that an electric force in one frame can be interpreted as the magnetic force in another frame. All right, so before I end this lecture, what I want to do is I want to first get rid of these circles, and then I want to tell you another surprising aspect of this above. That is the role of, this length contraction that we have seen. So we are used to thinking of this as some exotic result which is going to be important only when we reach velocities very close to c. But electrons in a wire actually move very slowly. They take maybe an hour to travel a meter. But on the other hand, you have seen that we can easily detect the magnetic force between two wires. So this magnetic force between two wires can be directly attributed to this length contraction of electron density, and so this is so you see that relativity has a role to play in very day-to-day life as well. This discussion above needs a minor alteration for actual wires. So in the rest frame of the wire, the positive charges, which are ions, which is with an atom stripped of their some of their electrons, these are stationary while the electrons move. And so this current is actually due to some battery feeding the electrons into the wire and taking them out at the other end. This is done in such a way that the wire is actually neutral in the rest frame. So in the same way, if we had moved in a frame where the ions and the electrons had equivalent opposite speeds, the wire would appear charged. So the starting point is slightly slightly different, but what we did, the physics remains the same. So an almost identical explanation works for that, but with this minor altercation. So I want to end this lecture today by saying that we have actually seen this whole thing played out in front of our eyes. That the forces. So what used to be an electric field in one frame becomes a magnetic field in another frame, and so this is something that we will try to make more precise, and we will try to understand the math behind it. The same way that you can look at. So you can look at Lorentz transformations, transforming electric fields into magnetic fields explicitly, and that is what we want to do in our next lecture. And so there will be a little more math, but I hope you have enjoyed this little lesson, and we will continuing trying to understand the special theory of relativity and its role in electromagnetism more clearly again in the next lecture. So that's it for this lecture. See you guys again sometime very soon. Thanks.